1 Lesson 9, Multiplying Polynomials. It's going to involve two instructional outcomes. The first one, understand that the product of two polynomials produces another polynomial, and we're going to continue with an outcome of multiplying various polynomials. At the end of the video, we're going to tack on one additional outcome not listed here, and so we'll look at pulling out greatest common factors and being able to write their various factors as well. So the purpose of this video is to provide a resource for both the parent and the student where both can review a lesson at home to improve classroom learning and provide improved homework understanding. So in exercise 1 that was discussed in class for this particular lesson, we look at a student, Gisela, who computed 342 times 23, but she did it in a way that we may not typically think about multiplying 342 times 223, because I know that if I was taught to solve it, I would have started by writing 342. I would have put times 23, and I would have gone through the motions that I would have been taught when I went through. But in this version, what we want the students to observe is what Gisela is noting as her 342, this being the hundreds place, which defines her 300. The 42 or the 40 here, and the 2 for the ones place. And the same thing for the 20 represents the 2, and then the 3 represents the 3 in this location. So what are we seeing Gisela do? What is our observation? Well, we know that 300 times 20 is 6,000. Same thing if I did my 40 times my 20, that's going to equal 800, and my 2 times my 20 will equal 40. Same observation. If we took this 3 and we multiplied it to the 300, then we're going to get 900. The 40 times the 3 is the 120, and the 2 times the 3 is the 6. So the students start the class to observe this, and the teacher's asking, can you explain what she is doing? And so these are some of the key characteristics we hope the students observe when they're seeing that. Now, at this point, the teacher, if the students haven't talked about this notion, is what's happening with these arrows. And so Gisela is keeping the 6,000, and she's going to move it here. She's then going to take this 800 plus this 900, and that's going to equal 1,700. This 40 plus this 120 is going to give her the 160, and then she's going to keep this last box that has no box up here to compare itself with, and keep the 6. And so at this point, what is the final answer? That's what we're asking the students to determine. Is they're going to take this 6,000, they're going to add it to the 1,700 plus the 160 plus the 6, and then they're going to come up with their grand total answer in that given perspective. Now in exercise 1, we're asking students to take and model this geometric diagram, very similar to what Gisela used in the opening exercise, but here we're going to apply, like we did a few lessons back, to where if I see this as 1, 2, 3 terms, so 1, 2, 3 terms by a 1, 2 terms, or a binomial times a trinomial for 3 terms. And so what we want the students to be able to do is draw a rectangle. If I was to write my 3x squared plus my 4x plus my 2 along the top, and my 2x plus my 3 along the bottom, I would take and divide this rectangle up everywhere I see a plus or a minus sign, across like so. So as in Gisela's example, we're going to do 2x times 3x squared to give us 6x to the third power. It's an important footnote to look at this idea of how we get x to the third power, where there's an exponential rule that states that if I've got a base raised to a power and it's multiplied to that exact same base raised to another power, then what we're going to do is take those two particular bases and add them together. As we did here, this exponent is a 1, this exponent here is a 2, and so 1 plus 2 would give us 3. In terms of the larger numbers in front, or the coefficients, those are multiplied as traditional, and students do not need to know a special rule for that. So let's try that again. For our coefficients, 2 and the 4, we multiply that together and we get 8. X times x, this exponent is a 1. This exponent is a 1, so 1 plus 1, and we have x squared. We'll follow up by doing 2 times 2 is 4. We'll multiply with that leftover x. There's nothing to add it to here. 3 times 3 is 9. There are no variables to combine, so we leave it as x squared. 4 times 3 is 12. Again, no additional variables to combine, so we leave the x. And then 2 times 3 is the 6. So what will we see done at this point is very similar to what Gisela had demonstrated in her version. We're going to keep this 6x to the third. It'll be a part of our final answer. We're going to add these two together, so 9 plus 8 is 17. We keep the variable design the way that it is. 4 plus 12 is 16. We keep the x pattern the way that it is, and then we keep the 6 at the very end. And thus we can say the solution, or the product, to multiplying these two polynomials is 6x to the third plus 17x squared plus 16x plus 6. And just as an additional reference, we'll note that the exponents are decreasing in value of 3 to 1, and then an x to the 0, which does not need to be listed in your final answer. So 1C and 1D, the setup will basically look the same. We see a 1, 2, 3 term polynomial, or a trinomial, times a 1, 2, 3 term trinomial. And so the students will end up drawing a box. It'll be more of a square box this time, where I will put 2x squared plus 10x plus 1, and then x squared plus x, and then plus 1. The difference is this time we'll have 2 divisions horizontally and 2 divisions vertically. So if we want to multiply, and I can line this up a little bit nicer, our 2x squared plus our 10x plus 1. And so if I filled it in, you would end up with 2x to the fourth. Remember, add the exponents. You'll have 10x to the third, and then you'll have 1x squared. In the next row, you'll have 2x to the third. X times 10x is 10x squared, and then 1 times x is x. In the final row, 1 times 2x squared is 2x squared. 10x times 1 is 10x, and then 1 times 1 is 1. So when we go through and we work our diagonal pattern, This one stays with our answer. So we have 2x to the 4th. This one right here, 2 plus 10 is 12. We'll keep the x to the 3rd power. The x squared plus the 10x squared plus the 2x squared, so 2 plus 10 plus a 1 is going to give us a 13x squared. 10x plus 1x is 11x, and we'll keep this last box as part of our answer. So again, I encourage you to try 1D on your own. See if you can work it out and make it the answer that you desire. I'll get you started by reminding you that if we have our x to the 3rd, our plus 6x squared, and minus 5, and then our x minus our 1, we will divide it up as such. So while I won't work this one out with you, I do encourage you to try it. And if you do need support with developing your answer, please see your teacher in class or email her for a confirmation of the answer, and your teacher will be more than happy to confirm. Likewise, what may be more familiar to some students is being able to demonstrate this product or this design without actually drawing the boxes, what we call the distributive property. So if I took this design, I could take this 3x squared and I could multiply it to x to the 4th, to the 2x, or the negative 2x, and then the positive 1. So I could say 3x squared times 1x to the 4th, I would end up with 3x to the 6th. Again, remembering that this 2 and this 4 will add together. I can start over. 3x squared times negative 2x. I'll get negative 6x to the 3rd power. And then 3x squared times 1 is a positive 3x squared. Noting that this first polynomial has 2 additional terms, I can take and multiply this one to here. So I would end up with a positive x to the 5th. X times negative 2x is negative 2x squared. And then x times 1 is plus 1x. We do have one more additional term to address, and that's this negative 1. So one more time, negative 1 times 4 is negative x to the 4th. Negative 1 times negative 2 is a positive 2x, and then a negative 1 times a 1 is a negative 1. So we have 3 parts here, denoted in red, blue, and purple. We're then going to go into each one and look for anything that's like terms. So here I see an x to the 6, so I'll scan. This is a 3, a 2, a 5, a 2, a 1, a 4, another 1, and this is an x to the 0 power, which has nothing listed there. So there are no like terms, so we'll keep the 3x to the 6. Here we have an x to the 3rd. Quickly we'll scan a 2, a 5, a 2, a 1, a 4, a 1, and no power at all. So we'll keep the negative 6x to the 3rd power. Here I see a 2. Here is another 2. So I can take and do 3, positive 3, minus 2. Gives me a positive 1x. We'll keep the squared. Here's x to the 5th. There are no other x to the 5th, so we'll write plus x to the 5th power. and then here is an x to the first. Here is another x to the first. So a positive 1 plus a 2 gives me a positive 3x. Here is a minus x to the fourth, and then minus a 1. Now, this is an acceptable answer when we combine the like terms. However, if we want to take this problem one step further, it is always nice to take these exponents and write them in order from least to greatest. So if we did that, the final answer would be 3x to the sixth. We would put our plus x to the fifth second, then our minus x to the fourth, minus 6x to the third, plus our 1x squared, plus our 3x, and then minus our 1 for our final answer, in that given problem. Next, on a side note, it'll be discussed in class the greatest common factor. In other words, the highest number that divides exactly into 2 or more numbers. So they did a DMR that day in class, and so they asked the students to think back. If we looked at 6 and 15, what did they say the GCF was? And the way the students determined that is they may have written down 6, listed all the numbers that go into 6, such as 1, 2, 3, and 6, and then they would have compared it to 15 and said that is 1, 3, 5, and 15. So what do we note? The largest number in each one that they have in common is the 3, and thus we'll call it the greatest common factor. The teacher then kind of suggested to students how do we deal with variables. And so if we know that the GCF of a 6 and a 15 is 3, and we have an x to the third and an x squared, the GCF of the variables will always be the smaller exponent of the two. And so in this case it would be x squared. So the full GCF would be 3x squared. For a deeper understanding of why x squared, if I had x to the third, that literally means x multiplied to x multiplied to x compared to x squared, which is x times x. And so what the student observes is that there is one pair of x's here and that there is one pair of x's here. And that is how this evolves into an x squared as part of our GCF. So in class, the students had an opportunity on whiteboards. They worked in small groups or in a pair, and they were given these sets of problems to see if they can come up with what the greatest common factor is. So if we looked at just a couple, if we looked at the 6 and the 14, the largest number that would go into both a 6 and a 14 would be a 2. And again, we hope the student can define that on their own, but if they can't, then they would take and they would write down the 6. And so they write down 1, 2, 3, and 6. They would compare it to the 14, which is a 1, a 2, a 7, and a 14. And again, how are these numbers generated? These are the numbers that if I multiplied them, they would go into 6. Like 1 times 6 is 6, or 2 times 3 is 6. Likewise, 1 times 14 is 14, 2 times 7 is 14. They will divide evenly into that. If we look at the A's, well, behind the 6 is an A, so that's only a single A. A squared means A times A, and I can only circle one pair. So if we look at the numbers, a 2 and a 2, our GCF would be 2 and then A. 2 and then A. They're asking the directions. Write down an expression that would be equivalent as if the distributive property had not been carried out, or basically the undoing of the distributive property. So if I know that 2A is the greatest common factor of 6A plus 14A squared, I can take this 2A, divide it into 6A. So mentally the student is thinking this: 6A divided by 2A, So the a's would cancel, and 6 divided by 2 is 3. Likewise, if I did my positive 14a squared, divided that by 2a, 14 divided by 2 is 7. Here's an a squared and an a to the first. So it may be important to note there's another exponential rule that if you have a base raised to a power divided by a same base raised to a power, I can really just subtract those exponents. So 2 minus the 1 gives me a single a left, and that's what I'm going to put in that parentheses as the additional factor. If I wanted to check and verify that my work was actually correct, then I could take this piece here, follow out that distributive property. 2a times 3 is 6a to the first power. You don't need to write the 1. And then 2a times 7a is 14a squared. So what we note and we observe is that that is what we originally started with. Here is our answer asked by the directions. So several of these work in the same idea. You would pull the GCFs out here, same thing here, and the other 3 as well. So again, I encourage you to practice these in further depth and understanding. And if you need any verification, just please see your child's teacher and get additional support. These were for more that the students were challenged with in class as well, in terms of writing down the same distributive property piece.